Alcohol deserves a special section all to itself. And this is because of all the molecules, all the poisons that have to be dealt with by forensic scientists. By far, it's alcohol that generates the most work. So alcohol is an interesting and controversial molecule. For some societies, for some cultures, alcohol is an essential lubricant that keeps the wheels turning. And yet in other cultures, it's an evil molecule which is reviled and must never be consumed. So this is a famous picture. This is a picture entitled Gin Lane, which was produced by the 18th century artist Hogarth. And it's intended to show the evils of alcohol. Well, actually, more specifically, it shows the evils of the very strong spirit gin, because at that time in England, gin consumption was enormous. Well, Hogarth actually wasn't opposed to alcohol itself. He just felt that consumption of gin was very harmful. And this picture is one of a pair. The other picture is called Beer Street. Beer contains much less alcohol and therefore is much less damaging than gin. And Hogarth and his friends wanted to encourage people to switch from one to the other. Now, what happens when someone drinks alcohol? Well, of course, the liquid goes down into the stomach. Some of it is absorbed by the stomach, and the bulk of it is absorbed in the small intestine. It's absorbed very fast. It will appear in the blood almost immediately, and it will be almost completely absorbed into the body within 1 hour. There is some variation of the rate of absorption depending on the kind of the drink and what the stomach contents are, but it's not a particularly big difference. Once absorbed into the blood, alcohol will be distributed throughout the body via the cardiovascular system, and it will, of course, penetrate into the brain. The blood-brain barrier doesn't stop it. And the effect of alcohol is actually to depress the central nervous system. Now, this seems a bit illogical because normally when people drink some alcohol, they don't seem to be depressed. This is because it's not depressing the person, it's depressing the nervous system. Part of that depression of the nervous system is the depression of inhibitions, and that makes people feel happier. But it doesn't just depress inhibitions, it depresses the ability to make judgments, it depresses the ability to react to situations, it depresses reflex times. And this is why alcohol, when combined with machinery such as motor vehicles, can be a very, very dangerous combination. Because of this danger, pretty much all countries around the world limit the amount of alcohol that can be present in a person's body while they are driving a motor vehicle. Now, the question is, how much is too much? What concentration of alcohol is there going to be in the blood after someone takes a drink? Because you don't know what's in your blood, all you know is what was in the glass in front of you. Well, we can calculate the likely blood alcohol concentrations from the amount of alcohol taken in. So suppose someone drinks something that contains a certain amount of alcohol. So let's say the amount of alcohol in grams is A. This amount of alcohol is then going to be distributed over the person's body. So divide by the person's weight in kilograms, which is P. However, as we shall see, alcohol is not distributed uniformly. So we have to allow for the fact that it's only spread over a certain proportion of the body. And so we have to put in a fudge factor. And this is called the Widmark factor. And there are different Widmark factors for men and women. So R, the Widmark factor, is 0.68 for men and 0.55 for women. And this is because Widmark considered that women's bodies have a higher proportion of fatty tissue than men's body. And that is a scientific and not a personal comment. So when we use this formula, we can calculate the maximum concentration of blood alcohol, C, as being equal to A divided by PR. So let's see how this works. Suppose you have a 70-kilogram man who drinks a double whiskey. How high is his blood alcohol concentration going to be after this? Well, if whiskey is about 43% alcohol and a single is 25 cubic centimeters, taking into account that the density of alcohol is 0.79 grams per cubic centimeter, then we can calculate that he has ingested 17 grams of alcohol. So if we put in 17 grams of alcohol in a 70-kilogram man, so the Widmark factor is 0.68, then we can estimate that the blood alcohol concentration is going to be 0.36 grams per liter of blood. So alcohol concentration is usually expressed as milligrams per 100 milliliters of blood. So when we correct for the units, this would be 36 milligrams per 100 milliliters of blood. Now, what is the effect of alcohol? In particular, what is the effect of alcohol on the brain? Now, different parts of the brain are not affected equally, so the effects vary according to the amount of alcohol. So below about 50 milligrams per 100 ml, for most people, there would be no obvious effect. As the blood alcohol concentration goes higher as the person has more drinks, then there are noticeable effects: loss of coordination, and of course, slurring of speech. Increase the concentration further, and these effects get worse. Marked loss of coordination, poor sensory perception, and in a lot of people, starting to feel ill and wanting to be sick. Say at 150 to 200 milligrams per 100 ml, now we have drunkenness, nausea, inability to stand up, and vomiting. So even after that, some people will keep drinking, and this will lead to coma, problems with the circulatory and respiratory system, and at high enough blood alcohol concentrations, this can lead to death. Now, alcohol has always been there in nature. For instance, the fermentation of fruits, which can occur naturally, means that alcohol has always been there as humanity has evolved. And therefore, our body has a biochemical mechanism for eliminating alcohol. In particular, there's an enzyme called alcohol dehydrogenase present in the liver and the small intestine. And this enzyme, alcohol dehydrogenase, will convert ethanol into a higher oxidation state molecule, which is acetaldehyde. Acetaldehyde is also toxic, so we have a second enzyme called aldehyde dehydrogenase, which will further oxidize that acetaldehyde to acetic acid. And acetic acid, that is naturally present as part of our metabolism. Our body can burn up acetic acid, and it will end up as carbon dioxide and be exhaled from the lungs. And almost all alcohol that is taken into the body will end up as carbon dioxide. A very small amount will be lost through the kidneys or breathed out through the lungs in the form of alcohol, the unchanged ethanol molecule. So when you smell alcohol on someone's breath, it's that small percentage that doesn't get burned up by the enzymes. Now, when the alcohol is in the body, it is pretty uniformly distributed. At least it's pretty uniformly distributed over all parts of the body where there's a lot of water. The parts of the body where there isn't much water do not get alcohol. That is the bones, the fat, and the hair. And this is the reason why we have the Widmark factor. There's a little difference between arterial and venous blood during the absorption phase, and that's simply because the alcohol hasn't been completely distributed yet. So in order to know how much alcohol is in someone's body, we can measure the amount of alcohol in any body fluid. So typically, blood alcohol is measured, and we can assume that whatever level of alcohol is in the blood, it will be the same level inside the brain. So to measure blood alcohol, a blood sample has to be taken, and then this can be analyzed by a technique such as gas chromatography, which we discussed in an earlier lecture. Now, to measure someone's blood alcohol level, this has to be done by a medically trained person. It has to be done in a proper place. But if a motorist is pulled over by the traffic police because he's driving erratically, how can the traffic police determine whether this guy's got too much alcohol? And the technique used is to measure the level of alcohol in the breath. Of course, if there's a traffic accident and someone's dead, then you can choose, as I said, any of the body fluids you like. Now, if the traffic police can measure the breath alcohol, how can we relate this to the blood alcohol, which is actually the important factor? The two are closely linked, and they are closely linked because of Henry's law. And Henry's law says that if you have a solution of something, a solution of a volatile substance in a liquid, then the vapor pressure, that is the amount of that volatile substance in the vapor phase above the liquid, will be proportional to its concentration in the liquid. So if someone has a lot of alcohol in their blood, then there's going to be a lot of alcohol in their breath. If they only have a little alcohol in their blood, there will only be a little alcohol in their breath. And these are strictly proportional. And that ratio is typically taken as 2,300 to 1. So you can measure the breath alcohol, multiply it, and then you have the blood alcohol level. Now, breath alcohol can be very easily measured, as we've said, at the roadside, using these kind of breathalyzer devices. And typically these breathalyzer devices rely on a little bit of chromium chemistry. Potassium dichromate is a very, very nice bright orange crystalline substance. Very nice color indeed. But if you take potassium dichromate and you have some acid present, and then you add alcohol, so this suspect motorist breathes into the device, the alcohol in his breath will react with the potassium dichromate, and the chromium is reduced and ends up as chromium sulfate, whereas the ethanol is oxidized to acetic acid. Now, chromium sulfate is green. It's a quite different color to potassium dichromate. And we can simply measure the amount of potassium dichromate that is converted to chromium sulfate by measuring the loss of absorbance at 420 nanometers. Well, it's not always as simple as just measuring the breath or blood alcohol levels. Suppose there has been an accident and one of the cars involved in the accident drives off and the driver is not apprehended until some hours later. Then you're not interested in the amount of blood alcohol the guy has at the time he's arrested. What you really want to know is how much alcohol was in his blood when the accident happened. And as we know, the body is working hard to eliminate alcohol from the blood. So what we need to do is to be able to calculate how much blood alcohol somebody had in the past, a certain number of hours after they are actually measured. So suppose someone takes a drink at time 0. Okay, at time 0, all the alcohol is in their stomach, none is in their blood. Very rapidly, that alcohol starts to move into their blood, so their blood alcohol concentration starts to go up. At some point, it will reach a maximum, and the biochemical machinery will be eliminating it. So it will reach a maximum and then it will drop off, and after some hours will reach zero. The question is, how steep is the slope of this graph? How fast does the body get rid of alcohol? Let's take an example. Suppose there's an accident at 3 a.m. The man is arrested some hours later, and eyewitnesses confirm that he had a drink before the accident. So the question is, what is his blood alcohol level at 3 a.m., the time of the accident? Well, suppose it takes 2 hours to arrest him and take him to a police station and take the blood sample and do the measurement. So we can only measure the blood alcohol level at 5 a.m. Now at 5 a.m., let's suppose that the measurement is 70 milligrams per 100 ml. So in most countries, including Singapore, 70 milligrams per 100 ml is below the legal limit. But what we need to do is to calculate his blood alcohol level 2 hours before at 3 a.m. We're going to do this two ways. The first way we're going to do this is using algebra. Now, what we need to know is how fast do people's bodies eliminate ethanol? Well, it's found that the slowest elimination rate is something like 12.5 milligrams of ethanol per 100 ml of blood per hour. So let's take the equation. Ct equals C0 minus T beta, where Ct is the concentration of blood alcohol at the time of measurement. C0 is the concentration of blood alcohol at the time of interest, i.e. the time of the accident. T is the time elapsed between the two, and beta is the elimination rate. If we rearrange this equation, then we get C0 equals Ct plus T beta. Now we can plug in the numbers. Ct is the 70 milligrams per 100 ml that was measured at the police station. T is 2, that's the 2 hours between 3 a.m. and 5 a.m. And the low elimination rate of 12.5 gives us a concentration of 95 milligrams per 100 ml. Now, people eliminate alcohol at different rates. So this is the calculation assuming a slow elimination rate of 12.5. A high elimination rate would be 25 milligrams of ethanol per 100 ml of blood per hour. So if we use the same algebra and put in this new value for beta of 25 milligrams, then we calculate that the concentration at the time of the accident is 120 milligrams per 100 ml. Well, whichever value of beta we use, in this case, the man was above the legal limit. If you don't like algebra, you can do it this way. If we assume the low elimination rate of 12.5 milligrams per 100 ml of blood per hour, 12.5 milligrams for 2 hours is 25 milligrams. Add that back onto the 70 that we measured, and you get the 95 milligrams per 100 ml. The same logic applied to the higher elimination rate of 25 milligrams of ethanol per 100 ml of blood per hour. So 25 milligrams times 2 hours is 50 milligrams. Add that onto the 70 milligrams measured at 5 a.m. and you get 120 milligrams per 100 ml. So however you do the math, you get the same conclusion, that this man was above the legal limit. So, as I said at the beginning, alcohol is the molecule that generates the most work for toxicologists. So, your good health.